to start with, I guess, one thing. First off, did you guys try the Riemann sum thing on the back of the sheet from last time? Did that kind of go okay? Uh, Taking it, nobody did it. Yeah, but it went okay. Yeah. Okay, so that one's a little bit of tedious arithmetic, but whatever. There's sort of 2 points that I want to make to start with that, which is one of the consequences of the assumption that our widths are always the same is means that mathematically we can get away with something. So let me just take, for example, where we left off with this formula here, the one I just circled. You see how we're adding up width times height, width times height, width times height, width times height, right? From a computational standpoint, it would be much more efficient to do this. Oops. Okay, and the reason I can get away with that is basically, well, if they all have the same width, why don't I just add up all the heights and then multiply by the width, right? That's called factoring. Yeah? Okay, which one's more efficient computationally? Yeah, doing the factoring, because then how many multiplications do I actually have to compute? Just one. Whereas with the thing that's circled, I would have to compute 4 multiplications on top of the 4 additions. Okay, and for the thing on the right, I would have to do the additions, but only 1 multiplication. So in terms of the number of arithmetic operations, I've really just cut the workload basically in half. Okay, and those of you guys who are, computer science types, this matters when you program a computer to do it. So mathematically, you're going to get the same answer basically, and so you might as well program it to do it the more efficient way, because that will save you like essentially 50% of your compute time in terms of your number of floating point operations. So anyway, okay. So the thing I wanted to start with today is actually to go through an example of doing the definition of the integral the long way, okay, in order to get some answer, okay. And for the sake of demonstration, I'm going to I'm just going to choose f of x equal x, and I'll choose a equals 0 and b equals, somebody pick a number, 3. Okay, whatever. That was kind of creepy. You guys both picked the same number. Okay. All right. So what I'm trying to find, of course, is this. Okay. And because of geometry, right, the graph of f of x equals x is just a straight line. I know that the area that I'm enclosing here is a triangle with base 3, height 3, okay? And so the area is going to come out to be 9/2, right? 3 times 3 over 2. Okay. But I want to go through the long way to see that this is in fact what it is. Okay, does that make sense? All right, so first thing I've got to do is set up my formula, okay? And I'm going to, for the sake of convenience, okay, I could do either the left-handed or the right-handed version. It doesn't actually matter, okay, because if, okay, so let me back up a minute. If I do the left and the right-handed version and I take this limit, what should the values of the limits be? Yeah, they should both approach the same thing. Okay, namely in this case 9/2, but in general the actual integral. Okay, so it doesn't actually matter whether or not I do the right-handed or the left-handed version, and the right-handed version is maybe slightly more convenient because it starts with 1 instead of 0, but that's basically the only difference. Okay, so I'll do the right-handed version. It'll make some of the arithmetic slightly cleaner, but yeah, okay. All right, so the setup I need, of course, delta x we said was b minus a over n, and in this case, that's just 3 over n. Okay, so that's the width of each of our rectangles. And the thing I'm trying to compute is the limit as n goes to infinity of the sum I equals 1 to n of width, which is 3 over n, times height, which is f of a, which is 0, plus I times delta x. And delta x, we just said, was 3 over n. Okay? All right, so that's the first step of the setup. The second step is, well, what is f of something? Yeah, f of x is x, right? And so f of this thing is really just the thing. So I can simplify considerably in this case. And so I'll have 3 over n times I times 3 over n, which I can go ahead and rewrite as the sum I equals 1 to n of 9 over n squared times I. Okay, and I'm going to copy this so that we can go to a new page with it. And actually, you know what, before I do that, let me go ahead and do this. Right, that's the same thing we just talked about a minute ago, right? I can multiply by the widths all at the end or do them as I go. It's mathematically equivalent, so I'll just throw them all at the end. Okay, so this thing is what I want to compute. Okay. Now we can already see that something's going right because you guys see the 9 already has appeared. Okay, so that's a good sign that we're on the right track. Okay. All right. So once Julia's just done scribbling it down, we good? Okay. So let me paste this in. Okay, that's what we want to do. Okay, so let me actually do something, a quick digression. Because we've got this limit and stuff to compute, but let's just figure out what this part of it is. And then we'll worry about the limit and the other stuff later. Okay, does anybody happen to know the formulas for the summations of the first n integers? Okay, I didn't figure, but that's okay. So what this is doing is adding up 1 plus 2 plus 3 plus 4 plus 5 plus dot 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 all the way up to n. Okay, so we would like to know what that is. And hopefully there's some very nice formula for it. There is, but what is said formula? Okay, so let me change the question for sake of demonstration. I would like you guys to compute that. 1 plus 2 plus 3 plus 4 plus dot 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 plus 99 plus 100. Okay, so how are you sitting thinking about how to do this? Well, okay. What's probably the worst way to do this? Okay, you don't have that many fingers. Okay, so there's that problem, huh? Well, that's okay. That's even worse than I could think of as being the worst idea, is using your fingers. Okay. But the worst idea would be to like sit down with a calculator and literally do 1 plus 2 plus 3 plus 4 plus 5 plus 6 and 7. Would it work? Yes, you would eventually get the answer. Okay, but that's not really a good move. Okay, there's a much smarter way to do this. okay? And it's to think differently. Did anybody say we had to add these in order? No, of course not, right? They're written in order, but there's no reason they have to actually be added in order. So I'm going to be sneaky, and I'm going to pair everybody up. How might I pair everybody up in a very clever way? Yes. Keep talking. Oh, I see. Won't quite work out. Okay, let's try that. Biggest and smallest. Okay, so because if I put 1 and 100 together, and I put 2 and 99 together, and I put 3 and 98 together, what does each of those pairs add up to? They all add up to the same thing. By 50, because how many pairs are there? Oops. Almost, yeah. Okay, so the formula is the top number times the top number plus 1 all over 2. Okay. Okay, now the way to think of that, right, is that we have however many pairs, okay, and each pair adds up to, well, in this case, like we were adding the numbers 1 to 100, all the pairs added up to 101. That's the n plus 1 term, okay? And furthermore, this formula still works if the number of things we're adding up is an odd number, okay? Because let's say we were adding up 5 things and we paired them up. There'd be a dude in the middle who was unpaired, right? So if I had 1 plus 2 plus 3 plus 4 plus 5, I'd put 1 and 5, 2 and 4, but then 3 doesn't have a partner, okay? But the formula still works, okay? And the reason, or a reason, is the division by 2. You might look at that and say, wait a minute, this means I'm not going to necessarily get a whole number answer, right? Well, I should get a whole number answer if I'm adding up integers, right? If I'm adding up a whole bunch of whole numbers, I damn well better get a whole number answer. Yeah? Okay, it doesn't make sense otherwise. Okay, but take the number n and the number n plus 1. If n is an odd number, then what's n plus 1? Okay, n plus 1 is therefore even. Well, even numbers are divisible by 2. Okay, and similarly, let's say that n is an even number, then what's n plus 1? But n is divisible by 2. So in either case, that fraction, one of the two things in the numerator is divisible by 2, and so that division by 2 is not going to be a problem. Yeah? Okay. Now, it turns out that this set of numbers that you get if you plug in a number for n in n times n plus 1 over 2, these guys are called triangular numbers. And they're called that because if I diagram what I'm doing, for example, adding 1 plus 2 plus 3 plus 4, if I lay it out with dots, it makes a triangle. Okay, so there we go. Triangular numbers. Okay, so this result we need because of what we were trying to do, which was that sum with the limit and the other stuff. Okay, all right, so good. All right, so let me paste this back here. Oops, and let's just plug in the, oops, no, I don't want orange, I want black, okay. Let's plug in the result that we just deduced, okay, for the figure at the triangular numbers. We need to compute that limit. Okay, and the sum is no longer there. That was the whole point of the little triangle business. Okay, so what would happen if we just multiplied everybody out in the top? We'd get 9n squared plus 9n. And in the bottom, what do I have? Yeah? No, it is, even though my coffee hasn't fully kicked in yet. It will. Okay, and so the question is, what is that limit? I mean, we know what it should be, right? Because we already know the answer. Oh, because we did the geometry at the beginning, right? Because in this case, we're just finding the area of a triangle, right? And that's not hard. Okay, so what is this limit? Well, what's the biggest power of n on the bottom? N squared, right? What about on the top? Same thing, okay? And so if we divide by 1 over n squared and go through the rigmarole, okay, in this case, since the powers are equal, the answer comes out to be 9 over 2, the ratio of the leading coefficients, which is exactly what it was supposed to be. What do you mean? Well, okay, the reason it was easier to do, and what was really the crux here, is this, right? If we didn't have that, we'd be boned, okay? And now this one was just for a triangle, or like a linear function, right? If we had done this with a quadratic, like x squared, we would have needed something a little bit harder, okay? Because this summation formula wouldn't apply anymore. We need a different one, okay? And they get progressively harder to figure out what those summation formulas are. Now they do exist, okay? And in fact, let's maybe do a parabola case because I've got some interesting history to share with you guys. Because I'm a nerd face. No. Right, because remember the analogy that we talked about at the end last time, right? Remember when we did the definition of the derivative, how ugly and horrible it was? And uh, then you were like, oh God, please tell me there are shortcuts. And then there turned out to be shortcuts. Well, kind of same thing here, right? Okay. So let's take another example. And let me actually do some geometry first and show you guys something. So I'm going to take a parabola. And just for giggles, I'll just pick plain old x squared, nothing special. And I want to compute, let me just say, -1 to 1, just to spice it up a little bit, okay? All right, so if I sketch this, right, of course we have this, and -1 to 1 would be that area in here, okay? Okay, so it's a parabola. Do we have some convenient geometry formula? Sadly, no. Or at least you don't. I know one. Okay, because, so let me draw the picture kind of blown up a little bit. And so I'll put one here, and therefore one is there. And then our parabola is like this. Okay, so we want to find the area that's underneath the parabola between it and the x-axis. Okay, so those two kind of wedgy looking shapes is the area that is in question. Okay, I want to find that area, but what I'm going to do is instead find the area that's inside the actual parabolic piece. And then I'll subtract that from 2 because what's the area of the giant rectangle? 2, right? So the thing I'm looking for is the sort of complement, if you will, of the stuff inside. If I can find the stuff inside, then I know the complement because I know what the total area is. Yes? Okay. So what I'm going to do is I'm actually going to construct the triangle that's in there. Okay. What is the area of that triangle? It's 1 because it's base 2, height 1 over 2. It's 1. Okay. Now, so the area of that parabolic piece, and in fact, let me write my triangle symbol upside down here. Okay, so the area of the triangle, that's easy, right? That's just some geometry. And that triangle I inscribed inside this parabolic segment, right? So it's not the entire parabola, it's just sort of a piece of it. Okay? Any guesses as to the relationship between that parabolic segment and that triangle? I mean, clearly the parabolic piece is bigger, right? But is there any magic number that relates the two together? And not quite 2. No, not, no. It's 0.14 wouldn't work. It's got to be a number that's between or bigger than 1, right? Oh, you just said 3.14? Okay, sorry. That's too big. Yeah. How'd you guess that? Because it is, in fact, 4/3. Okay. Well done. Well played, sir. It is 4/3. Okay. So the area of this parabolic segment turns out to be 4/3 of the area of, oops, sorry, that should be the letter A, and this should be a triangle. Okay, yeah. What number am I thinking of right now? No, 17. Yeah, yeah. Okay, so the area of that triangle is 4/3. Now, you could eyeball it, right? Or if we drew this on graph paper or something, you could maybe estimate that yeah, 4/3 is actually a pretty reasonable number. Okay, but how do I know it's exactly 4/3? No, because it's a parabola, not a circle. It's because I've read a lot. Okay, Archimedes actually proved this. Okay, so Archimedes showed that if you have a parabolic segment and you inscribe a triangle in it, the area of that parabolic segment is 4/3 the area of the triangle that you inscribed, always. Okay, so 4/3 is in fact that magic constant. Okay, now the crazy thing is, how did he do it? Well, mathematical wizardry, right? So he actually gives two different proofs of it. Okay, now one of them. Where's my engineering physicist type people? No? All right. Well, I'll give you the short story then. Um, how many of you guys, when you were in elementary school, there was a seesaw on the playground? Or are those no longer okay? Yeah. Okay. Yeah, they were. Okay. So you had a seesaw on the playground, right? So what happens if you put 2 kids, one on either end? Well, it depends on how big they are. Okay. So let's say that you've got a real big kid on one end and a real small kid on the other end. What happens? The big kid goes down and the little kid's way up in the air. And if this happens fast enough, you could actually launch the little kid and, right, this could be kind of fun, right? Well, probably. Okay. Now, why is it that the big kid went down and the little kid went up? Yeah, because he weighs more, but there's one other assumption there that you've made, namely that the seesaw is constructed so that the distance from the hinge in the middle to either end is the same, right? It'd be kind of a weird seesaw if it weren't made that way, okay? But what about, and did anybody ever try this when you were a kid, right? put the little kid at the end, and then get the big kid and see where along the bar he had to sit in order to perfectly balance the little kid. Did you ever do that? Yeah, you were doing physics. Yeah? Okay. So it turns out that the things will balance if the ratio of the masses is inversely the ratio of the distances. Okay. So if you put the big kid, let's say the big kid is twice the weight of the little kid. Okay, just say. You'd have to put the big kid halfway of the distance to the fulcrum, the hinge, that the big kid, or that the little kid was. Right? So if the ratio of their masses are 2 to 1, you want the ratio of their distances to be the inverse of that, 1 to 2. And then they'll balance. Okay? That's called the law of the lever. And Archimedes knew this. And so what he actually did in sort of a mathematical conceptual way is he said, okay, I'm going to take this triangle and I'm going to put it over here. And I'm going to take this parabolic piece and I'm going to put it over there. And then I'm going to pretend that these are little kids on a playground balance and figure out what's the ratio of the distances that makes the parabolic piece balance the triangular piece. And he found that those distances, the ratio was 3/4, and therefore the ratio of their masses or areas had to be 4/3. So he used sort of a mathematical balance, like doing it on paper, kind of the idea of a balance. Now, I would guess that he might have actually done an experiment with this, where he had a parabola and a triangle that he cut out of wood or something, and then literally tried to balance them to see that it was about 4/3. Okay. And then sat down and did all the math. Okay. So he didn't use, like, in his book, he doesn't describe using a literal balance, or it's not a book, it's just a short work. He doesn't describe using a literal balance, but I wouldn't be shocked if he had sort of done that. Okay. But in the math, he does sort of a conceptual balance, right? And what he does is he carves up the shapes into a bunch of teeny pieces, and he shows that each piece balances with the corresponding other piece, and therefore the whole things will balance with the whole things. It's brilliant. Okay. Um, yeah. So that said, I know that the area of that parabolic piece is 4/3. Okay, because I've read Archimedes. Um, Now, that's not the area I was looking for, though. What was the area I was looking for? Yeah, the stuff that's actually underneath the parabola. I found the stuff that's inside the parabola. Okay, but what do I need to do? Subtract from 2. Okay, 2 is, of course, 6/3. And the stuff I don't want is 4/3. And therefore, the thing I'm looking for is 2/3. Not that I'm aware of. Well, okay. You'd have to decide, well, what are you inscribing? Okay. So yes, there is, but at this point, it's okay. So let me back up a moment. Like, let me back up half the semester. Okay. When we started drawing tangent lines to curves, right? Well, I could just kind of sketch it, but we wanted a general procedure to know what the slopes would be, right? Okay. And the first example that I showed you that was non-trivial, well, there's two good examples that I could show you that are non-trivial. A circle and a parabola. Right? Didn't I showed you guys how to do the tangent to a parabola without any calculus? I know I did. Well, let me draw it. Okay, so let me take the case of the circle and the case of a parabola. Oops, that's the worst parabola ever. Okay, if I want to, so let me pick a point on this circle. I want to draw a tangent there. How do I do it? I'm going to connect that radius and draw a perpendicular at that point. Okay? Euclid Book 3, Proposition 16 says that tangents meet the radii at right angles. Okay? All right, for the parabola, what? Kind of, yeah. To the Pythagoreans it was. So you're laughing because it was Book 3, Proposition 16? Yeah? Okay. So, and in fact, it's not a complete hyperbole to say that Euclid Book 3, Proposition 16 says, for Euclid did so love the circle that at any point on it he gave its only tangent. Okay. Yes. Okay, and I was just riffing off John there if you didn't catch the reference, but you know, Hutos gare gapisen, hotheos ten gain, edoken ten monogenein, ten, or, yeah, so, no, that's it in Greek. Okay, so, right, for the parabola, I did something else. I picked a point, I've got my axis, and I dropped a perpendicular, and that cut off a segment, which I'm going to highlight in green, which is called the abscissa, right? The part cut off, literally is what that means. And I'm going to double it to a new point here, and then I'm going to connect that new point and my original point of tangency, and that's how I constructed the tangent. Well, it's because I used the iPad tool. Right? Okay, so this works perfectly well for circles and parabolas, but what about other shapes? This is too bespoke, if you will, right? It's not a general procedure, okay? The limit definition gave us a more general procedure. Similarly with this area stuff, okay? Yeah, I might be able to do it for a cubic and figure something out, but then somebody's going to come along with the hyperbola and I got to throw everything out and start all over. Well, that's not going to be a good approach, okay? There's got to be a more general way, and it turns out there is one, okay? Okay, so, right. All right, so for back to this problem, what was our A? It was -1, okay? And our B was 1, and our N, or sorry, not N, our delta X is, so actually, let me change things slightly. Do you guys agree that there's some obvious symmetry here? So why don't we go from 0 to 1 and then just double our answer? Okay, that'll make the arithmetic work out a lot cleaner. Okay, and so then our width is just 1 over n. Okay, so the limit I want to compute is this. I equals 1 to n of base, which is 1 over n, times height, which is 0 plus I times 1 over n squared, because I'm doing a parabola in this case. Okay, so let's simplify everything. And so what do we get? We've got I squared over n cubed. And I'm going to, like before, pop the n cube, or the n part outside. And so that's the summation formula we need. Okay, good so far? All right, so side note, this one is not nearly as easy to see why it's true. But you guys can trust me. Okay, the sum of I squared turns out to be n times n plus 1 times 2n plus 1 all over 6. Originally Archimedes, although he didn't write it this way. Like, he expressed the idea in a very different way. But he needed this result in a different one of his works, which was on spirals, where he's trying to find the area enclosed by a piece of a spiral. Like Archimedes? Yeah, we do. We have people like Einstein. Like more like a little over 100. Well, yeah. Well, so who are our geniuses in today's world? Okay, Elon Musk. Yeah, you just don't know about them. Yeah. I mean, okay, so there's actually one guy. Let me show you his picture because he's kind of crazy. Okay, so there's this guy, for example, right? Uh, Cedric Villani. He's French. Um, he also has the award for the world's best dressed mathematician because he dresses sort of like in 19th century garb. I've never met him, but I mean, the hair could use a little bit of work, but thanks. Okay. Yeah, he has, it's like this spider brooch thing. So, yeah, he's a wizard, Harry. Okay. So, um, yeah, anyway, there are mathematical geniuses, or another guy, um, Perlman, what's his first name? I'm blanking. He solved basically a several hundred-year-old math problem, um, and uh, basically lives with his mom in Russia. And yeah, or Andrew Wiles, excuse me, who solved the following problem. Well, or you become a math major, right? Okay, so you guys all know Pythagoras' theorem, right? A squared plus b squared equals c squared. And there are a whole lot of whole numbers that solve this, right? So for example, 3, 4, 5. Okay. So what about if you change the exponents and you say, okay, I want to have the sort of equation that looks like Pythagoras' theorem, but is in fact a different exponent, okay? Now this may not correspond to anything geometric, but let's just experiment with it, okay? So let me say that the exponents are cube. So a cubed plus b cubed equals c cubed. Your job is to find whole numbers that solve that equation. Oh, and by the way, using 0 is not allowed because that's too easy, right? All right, 1 cubed plus 1 cubed equals not 1 cubed. Try again. Mm-hmm. Turns out there are no solutions. Hmm? It's a stupid problem that there are no solutions to this? Huh? No, well, he was able to prove why there are no solutions. And there are probably 10 people in the world that understand that proof. Like it's that big. So this that there are no solutions to this is called Fermat's last theorem, okay? Named after Pierre de Fermat, French mathematician, 17th century. It was not until like the early 90s, 1990s, that Wiles finally, after 300 and something years, cracked it, okay? Now, why does it matter? It turns out a lot of the math that went into solving it has to do with things like, well, elliptic curve stuff, which can also be used for encryption. Okay, and now Fermat, what made him think of this? Well, Fermat was sitting around and he was reading a book by somebody named Diophantus, another Greek, big shock. And Diophantus was interested in, amongst other things, when can you have sort of equations, if you will, where you're only allowed to use integers for the variables, what kinds of solutions happen? Okay, so anytime you're taking what otherwise would be a normal looking equation and you're going to say, okay, I only want to know solutions that have whole numbers for the variables, not going to include fractions or anything. We call such equations Diophantine equations, okay? And solving them can be really quite hard, or finding those solutions can be very hard, okay? So this is an example of a Diophantine equation. It's a particular kind of category of them. And Fermat was reading Diophantus, a copy of it in Greek, no less, because, well, back then you just would, right? And he scribbles in the margins, I have discovered a remarkable theorem that this has no solutions if n is 3 or bigger, but the margins are too small to contain the proof. And then he eventually died, and it sat open for 300 years until Wiles finally cracked it. And let's just say that Wiles' proof would not have fit in the margins. Okay, so anyway. So yeah, you don't hear about these people necessarily nowadays, but well, you don't hear about the mathematicians, right? But what about the physicists or the engineers or okay, so there's really two things, right? One is that the big works, the things that are going to be, famous, take a lot more people than just one person anymore, right? Einstein was able to figure out relativity, but modern mathematics, modern physics, all happens with groups, right? Almost nobody is like living in a cave doing math or physics or anything anymore. Okay, so there's that. Um, but all like the big engineering projects or things that you would hear about, right? Well, they're done by teams, and yeah, you might know who was the project director. So it's kind of like, Elon Musk, right? You mentioned him. Is he really the genius there? He's the entrepreneurial genius, but is he the engineering genius? No. But what he does have is an uncanny knack for how to hire the engineering geniuses and get them all together and give them the stuff that they need, money and otherwise, to do truly remarkable feats of engineering, right? Cars, but most especially rockets, right? He's just revolutionized the space industry. Um, Oh yeah, yeah. You have to know some things, right? This is why, like those of you guys who want to go into like management or business or something like that, like it will be very obvious in 10 seconds of conversation with somebody who knows what they're talking about, whether or not you know what you're talking about. Okay, and you don't want to be the idiot manager that doesn't know what they're talking about. Okay, so does he know every little, gear and tooth and whatnot detail? No, but he definitely knows well enough detail to keep the ship running. Okay, um, and hire people that not only can do stuff but explain to him, okay, we want to do this because of blah, or we could do this, but we think this is right. Like they've got to be able to explain to him why they want to do something, and in enough technical detail that it's correct, but also not, you know, yeah, oversimplifying. Okay, so um, yeah, so I mean, there are these people today, right? I guess part of it, though, too, is that um, there are a lot more people you hear about in the news today, right? What would have been your source of news 100 years ago? Radio and the newspapers, right? That's basically it. And whatever word of mouth you would hear. Okay, but you weren't carrying around Facebook in your pocket, and you wouldn't have known necessarily for a couple of days that Will Smith had smacked somebody at the Oscars or whatever, right? If you care about such things. I do not. But yeah. Okay. All right. So back to our problem. And then we'll quit. Which is just take this summation formula on faith There's the religion part. Okay, and that's the limit that we need to compute. Now, if I were to multiply everything out here, what would be the coefficients of the in? Well, first off, what are the powers on top? What's the biggest power on top that'll appear? N cubed. Okay, you see n, but it's because it's broken into three pieces. It would be n cubed. What's the coefficient? Okay, what about in the denominator? What is it? Okay, and then that's really only half of the answer because I cut the region in half for simplicity. Okay, it would really be double that, but that's the same 2/3 that we got a minute ago. Okay, does that kind of make sense? Okay, so what we'll start with on Monday is looking at basically developing the more general procedure, okay, for how to do this and how to do it for essentially any curve, okay, with any function. Because what we've done so far is still too bespoke to be a generally useful. Okay, and what we'll end up finding is, courtesy of a thing called the fundamental theorem of calculus, is that the idea of, okay, so we've used the integral symbol in two different ways so far, right? What was the first way we used it? Okay, and the second way we did it was with this area stuff. You would guess by the fact that we use the same weird symbol that they might have something to do with each other. And it turns out that they do, and that's why we use the same symbol for both of them, okay? And so it will turn out that this general procedure will have something to do with the antiderivatives, okay? And we'll look at those details and stuff next week. Yes. Yeah. Okay. Now, for IQ, there are formulas for these summations for I cubed, I to the fourth, and so on, but they're a lot harder to see geometrically why they're true. So, anyway. Okay, let me quit the stream.